Okay.
Just
Let me also resume the recording. Great, thanks. Thank you everybody for attending today to the IEOR-DRO seminar. It's our pleasure to have Jose Correa visiting us from Chile. Jose Correa is a professor of operation research at the Department of Industrial Engineering at the University of Chile. He obtained his PhD from MIT, and also he's a researcher with the Center of Mathematical Modeling, and also an invited researcher at the Institute of Complex Engineering Systems. So, Jose, we're happy to have you. Please take it from here.
Thank you, Santiago. Cool. So, thank you for the invitation. It's been a pleasure to talk to some people, some new people and some old people in this morning, and I see that I will be continue talking to people this afternoon. So it's a great pleasure to be again at Columbia, although virtually, but still it's nice. So I will actually talk about some recent work I was doing with my student Andres Christie and my postdoc Laurent Fayollet. Yeah. So is there? No, that's good. Okay, my postdoc Laurent Fayollet and a visiting student Alexandros from TU Munich, and Tim Ostervik, who's a professor in Maastricht and was a postdoc of mine a couple of years ago. So this is basically, we're going to look at the secretary problem, and with some small twist, and we'll see that the problem becomes quite interesting with this twist. So let's get started. So first of all, I will tell you about some motivation for the problem, some different kind of optimal stopping problems that are appearing a lot in recent work, particularly in the last, say, 10 years. Then I will explain you this idea of sampling in these optimal stopping problems. Why is having additional information is interesting, either in the form of distributional information or sampling. And then I will explain you the results. I will try to give you an idea of what we're doing in this paper for the random order secretary problem and for the adversarial order secretary problem. So, okay, so the work lies within the framework of sequential decision making under uncertainty, which is, I would say, some very classic problem from several fields. In computer science, people have been looking at online algorithm in which you have the input that is revealed online for already many years, and there the main paradigm is to study the worst case analysis, like what if an adversary is setting up the input. From the OR applied probability community, this has been also studied for a long time. But there, like, the typical question is, what happens if the input, instead of being adversarial, is stochastic? Somehow there is some distributional assumption behind the data that's coming, and we have to make decisions on the fly. And also in game theory, people have studied this since the work of Shapley, I guess, when they look at stochastic games, in which, depending on the actions you make, then things happen, and then you need to make new actions, make new decisions, and there are additional strategic interactions. But even stochastic games with one player are interesting. So are studied in game theory. These problems have several applications in economics, finance, in pricing American options, for instance, in search theory in economics, in resource allocations, in e-commerce for this posted price mechanism, etc. So I'm not going to get into the many applications, settings, because I will in the end talk about a very simple problem. So I don't want to, like, the applications typically have more ingredients in the problem. So, but let me tell you a little bit of the history of the problem. So, of the secretary problem in particular. So I guess the first reference to this problem comes from Kepler in 1613. So Kepler was looking for his wife passed away, and he was looking for a second wife, and he writes this very interesting letter that I invite you. I mean, you can find it easily online, this letter, in which he tells his story about finding a second wife. So he set up a very methodic process. He interviewed within a period of 2 years, 11 won, and he was not really making online decisions because he interviewed the 11 candidates, and then proposed to the 5th candidate. So for people that are knowledgeable in the secretary problem, they will realize that this number 5 is pretty good, actually. So if he could have saved like more than a year of interviewing people if he knew what we know now, like this. So then there is a much more precise description of the problem, comes from Arthur Cayley, one of the most prolific mathematicians of all times, who proposed the following problem. So he proposes the following problem. So a lottery is arranged as follows. There are n tickets representing some quantities, and a person draws a number, look at the ticket, and can draw again if he wishes, out of the remaining tickets, of course. In total, you can draw at most k times, and you receive the value of the last ticket drawn. So here it's really an optimal stopping problem. So like a sequential selection problem. You really look at the numbers sequentially until you decide to stop. And this is not really the secretary problem, but it has a flavor of it. And there is a limit version which was posed by Moser in the 50s, in which he says, what if we take the limit in Cayley's problem? So n is very large, and k is now n actually. So n is very large, and therefore somehow what your drawings are random, uniform, independent samples from some distribution, and you can draw up to k times in Cayley's problem, but Moser uses n for this number, and until you decide to stop. And of course, the problem is fairly easy to solve using dynamic programming, but getting explicit rules for different settings it's much more complicated. So this actually leads more to what we know as the profit inequality. So in the profit inequality, which was a very classic topic in the 70s and 80s in the probability theory community, you have the following setting. You have n independent and non-negative random variables. Each one is, say, xi is distributed according to fi, and we have a gambler and a prophet. So the prophet can foresee everything, and then the prophet can pick the maximum of the realization, the maximum value. But the gambler has to look at the instance sequentially and has to maximize the expectation of what he picks. And maybe the most well-known result for profit inequality is this 1/2 bound that by Krengel and Sucheston in the 70s, in the late 70s. And basically what they prove is that the optimal stopping rule, which is essentially just an online algorithm. So the optimal online algorithm can get in expectation half of what the prophet can get. And this is best possible. And then there is several follow-up work. In particular, Esther Samuel-Kahn proves that this can be done with a very simple rule, with a very fixed threshold algorithm. So this is a very classic version of optimal stopping problems. And it's interesting because of more recently discovered connections with posted price mechanisms. So now imagine the setting in which you have n potential buyers with independent valuations. And now you have the benchmark would be, instead of the profit, like the new profit would be Meyerson, and Meyerson tells you how to compute the optimal revenue, the mechanism achieving the optimal revenue. That's one thing. And on the other side, you have what we call a posted price mechanism, which basically says now customers arrive in some order, and you can only make take it or leave it offers. So you make every customer a take it or leave it offer. They can either take it or leave it. And what you get is the price paid by the customer that bought the item. Now, the problems look similar, but they're not completely equal. But you can prove actually that these are equivalent things, like the profit inequality and this posted price mechanism design, they are equivalent. But this is another type of optimal stopping problems, and depending on the complications that you add to the problem, they can be a bit different. And then there is, of course, the secretary problem. and which is the topic of this talk. So in the secretary problem, you have n candidates that arise sequentially, and you want to maximize. So the values now are not distributional, like they are arbitrary values. So the candidates have arbitrary values, which we use alpha 1 to alpha n. And you observe the sequence sequentially. The sequence typically comes in random order, but we'll also see the adversarial order case. And you have to pick the maximum. And the secretary problem even made it to the news in Chile a couple of years ago, where they were suggesting that you need to have 12 couples and discard all of them, even if one is Brad Pitt. So that's what the newspaper says there. Okay, so this problem is, I guess, very well known. The solution of this problem has been known since the 50s, actually, and the first published paper about this is from 61. But there are many, I mean, it's actually unclear who was the first person to solve the problem. Many people attribute it to Robbins, who was a professor at Columbia in statistics in the 50s. And the best possible algorithm is very simple. So you look at the first n over e values, so roughly 37% of the values, and do nothing with these values. And after that, you select the first value that's larger than everything you've seen. Cool, simple algorithm. The probability of picking the maximum of the whole sequence with this algorithm is actually almost 37%. In adversarial, and this is in random order, of course. In adversarial order, nothing can be done, really, because the adversary, I mean, the best you can do is basically pick an element at random, and then the probability that you win is like 1 over n. So there's no constant guarantee for sure. Cool. So what happens if we add information? Like we take, now we're gonna fix the secretary problem. So this is the problem I'm looking at. I have candidates that arrive in some random order, and I want to pick the maximum. That's gonna be my problem, but I will tell you a little bit more about what happens with additional information in the profit inequality and in the secretary problem. So what if we have distributional information? So there is this paper that, I mean, once you have thought about the secretary problem, a very natural question is to say, so what about the case in which the values, instead of being adversarial values, like whatever, arbitrary values, are samples from some distribution? And this was a question that was answered by Gilbert and Mosteller in '66. They look at the secretary problem again, and they say, now the values are IAD samples from some known distribution. Of course, when you have this, you can run a dynamic program. If I'm standing at the last value, I will pick it for sure, so long as it's the maximum so far. If I am in the previous to last, then I can, given the value that I see, I can compute the probability that this guy is the maximum, and I take it or leave it depending on this. And then I can compute the optimal policy by dynamic programming very easily. What's not so easy is to actually analyze this optimal policy, and that's what Gilbert and Mosteller achieved. And they proved that in the worst case, you are success guaranteed, so the probability that you actually pick the maximum is almost 60%, so 58%, and it's the solution of some equations, of course. It's not, I mean, it's not a numeric value, right? If the values are now independent random variables from known distributions, but not IAD, like different distributions, the optimal guarantee is actually not known. That's an open problem. And it is known that with a single threshold algorithm, so basically you pre-compute some magic threshold out of all the distributions that you know, and it's a recent result proves that with a single threshold, you can achieve already a pretty good guarantee in this problem, in this random order, but non-IAD, so independent values. The optimal guarantee is open, and so that's not solved. And another cool recent result, a relatively recent result, is what happens in this problem in adversarial order. So now it's not IAD, it's independent values from different distributions. But the order in which they are presented to you is adversarial. So you know all the distributions. And you know that an adversary, I mean, this is a game in the end. There is an adversary that's selecting the order in which he's going to show you the realizations of these values. But of course, the adversary doesn't know the values, right? I mean, just knows the distributions. And in this case, the optimal guarantee is surprisingly, again, 1 over E. I mean, this 1 over E apparently has nothing to do with the 1 over E of the secretary problem, but it appears to be the same. And it's also a single threshold algorithm. So this is again, interesting. And we'll see some connections with these results later. Now, what about samples? So if you think about samples, it makes more sense to think about the profit inequality, because there, all the results we know are, I mean, most of the results we know are for distributional settings. So we have distribution, random variables according to some distribution. So the question that people starting to ask about, like, since this paper by Azar, Klein, and Weiber in 2014 was, what happens if instead of knowing the distribution, I have samples from these distributions? And there are a bunch of results along these lines. In particular, with Paul Duting, Felix Fischer, and Kevin Schwartz, we proved that if we know that your values are IAD, but you don't know the distribution, then you need a linear number of samples to beat 1 over E. So to do better than the simple algorithm that you would get from the secretary problem, you need a linear number of samples. If you have little of n samples, then there's no way you can beat 1 over E. And there are similar models and several results. One interesting model, I think, is by Kaplan, Naori, and Russ in Soda last year, in which they say, suppose we have values which are arbitrary values, and we get to, the values are, say, come in random order, are randomly sorted, and now you get to see half of them, or a fraction alpha of them. And now you have to play the profit inequality game. Somehow you have to solve the optimal stopping problem in the remaining values, in the values you didn't get to see. And this is it's a very rich model, and there you can prove you can do 1 minus 1 over E, and even better than that, which is what basically you would get for the profit inequality. So basically you lose just a little bit to the case in which you would know the distribution of the values. An amazing result, I think. I find this fourth line, and it's pretty amazing. An amazing result is the following. So in the classic profit inequality, your optimal guarantee is 1/2. And there is this recent paper by Rubinstein, Wang, and Weinberg that proves that if you have one sample from each distribution, exactly one sample, you can get the optimal guarantee. This is, I would say, very unexpected. So typically you would expect to have lots of samples, so to be able to learn the distribution, and to be able, I mean, in order to achieve the same guarantee that you would achieve if you knew the distribution. But for the profit inequality, just one sample is enough. And this is, I think, something very nice, and it's a very nice paper. Okay, so what is our problem? So our problem is very much inspired in this Kaplan et al. Paper in Soda 2020. But we have some things that make it a bit simpler, and also the objective is different. So we have our set of candidates with values alpha 1, alpha 2, alpha 3, and so on, and we don't know these values. And there is some sampling probability P. So the first thing that happens is that each element is sampled with probability P, and we get to see it. So we take all the elements with probability P, the elements belong to the sampling set. With probability 1 minus P, they belong to the set of values of non-sample elements, and we get to see the sample set. Okay, and the order of the set V is random. It's a random permutation of these guys. So the set V of non-sample elements are shown in some order sigma that in principle is going to be random. So again, we scan the elements in V, one after the other, until we decide to stop. And we win if we get the maximum of the set V. If we get the maximum of the set V, we win, right? That's the our online set somehow. And we want to maximize the probability of picking the maximum. So is the problem setting clear? I think this is a point where you could stop me if it's not.
Just a quick question: are the alphas originally they're samples from a distribution, or they're arbitrary, or what?
They're arbitrary. Yeah, they're arbitrary, just like in the classic secretary problem. So these are you can think that an adversary wrote these values.
Got it.
Adversary that one.
How does, so if they're truly arbitrary, how do the sampled elements give information about the non-sampled elements?
Yeah, that's the cool fact,
all right.
right? Yeah, I agree. That's the interesting part of the story. Yeah.
And how is the order they are presented again? Sorry.
The order could be random or adversarial. I will start by looking at the random order case.
Hey, sorry, Jose, I thought I understood, but after the exchange with Siamak, now I'm confused. So when you sample with probability P, is this IID with probability P?
Independently with probability P, yes. Flip independent coins for each potential candidate. And if it's heads, then I include it into the sample set. If it's tails, I include it into the online set, into the set V that I call V of values, right?
Yeah, okay. I mean, so that's why the sampled elements can say something about the unsampled ones, because you're picking IID, right? Okay, I'm good. Thank you.
Yeah. No, that's...
One more question. I could have imagined that I would be presented the set V and S together in some random order, and then try to choose the maximum of the total. But here I'm just looking at the V online ones and learning, using S just for learning.
Yes. So
is there some natural implication in one direction or the other between those two models?
Yeah, that's a good question. I don't know, actually. So the logic behind the model is that your set S is sort of your history set, right? You have some historical data that in principle looks like the data that you're gonna face today. And that's the rationale behind having S and V being sort of sampled independently.
So I could think of this as...
But I think, yeah, your question makes sense. Yeah, I don't know.
So your model, at least, I could think of as the classic secretary problem, where all algorithms are constrained not to pick the first size of S elements, basically. And then I'm benchmarking against that.
Are constrained and not picking. Yeah, exactly. And that's, yeah, you will see that this is essentially what we are doing. Yes, absolutely. Yeah, so you get to observe some number of guys, and these guys, you just observe them, right?
But that will be only true under the uniform random permutation model, correct? If the permutation is adversarial too, that's not the case, correct?
Yeah, so in both cases, we look at the sample elements are random, are like a random set, like in which I look at each one with probability P. The adversary chooses the order of the set V, not of the set S.
I'm commenting that on the last line, you also talk about like the permutation being uniform or adversarial too.
Yes, exactly, yeah. Yeah, fine. No, but what Nick was saying is that this is like I am forced not to stop until I see all elements in S, and they come early, right? And in the adversarial setting, it's a bit different, right? In the random order setting, this makes sense and perfect sense, right? And in the adversarial setting, it's slightly different. Okay. Cool. So problem is relatively clear, apparently, at this point. So let me. So these are the results we obtained. So we obtained the best possible algorithms for both orders and any value of P. That's the main contribution. And I think that I mean, probably two interesting facts to observe. So one fact is that, okay, of course, when P is 0, like, do you see my cursor here, I guess? Maybe not so well.
Yes, we see it.
Okay, so when P is 0, and so this dashed line is the adversarial order. So this AOSP is the adversarial order. Sorry, no, and the dashed line is the random order. Okay, of course. So when P is 0, the guarantee is 1 over E because it's just a secretary problem. So this is should be very clear. And then it grows essentially linearly. And when P goes to 1, what's interesting is that your guarantee grows to that of Gilbert and Mosteller, which is the value you get if you knew that if these were IID samples from some distribution, some known distribution. So the intuition behind that is that it's roughly the following, but I think the intuition is not so fantastic. So N is very large, think that N is very large, and draw the empirical distribution of the values that the adversary wrote. And now I'm sampling a fraction 1 minus epsilon of this. So this means that I have now pretty good knowledge of the actual distribution of the values. And the problem is that these are not IID samples from this distribution. These are just fixed values, right? So there's no replacement. But even if that happens, and the fact that you only sample a fraction 1 minus epsilon of the values, your knowledge of the distribution is good enough so that you can achieve this optimal factor. So that's basically what this is saying. And the connection here is even more intriguing. So for the adversarial order, when P is 0, of course, you do nothing. Okay, that's fine. But when P goes to 1, you go to this 1 over E, which is the guarantee that this paper by Alart and Islas get, which is the case in which you have full information about the random variables that come in adversarial order. But I cannot really write the connection between our 1 over E and their 1 over E. They look very like closely tied. I mean, I don't know. There should be some good connection there, but I cannot find it. Like, seriously, I don't have a good intuition on why that's the case. So, and again, we also do it with a fixed threshold algorithm. So it really looks like there should be a stronger connection there, but that's, to me, something I don't fully understand, I think, yet.
Are these
okay, so this,
sorry.
Sorry?
A quick question. Are these success guarantees independent of the initial number of items N?
No, they are, yeah.
So this is like the large N limit or something? Okay, they're independent of that.
But they are in, yeah, I mean, the worst case is when N is very large, always.
Okay.
But yeah, so you can get the same guarantees for small n and it works. Yeah, so these are the worst case guarantees, which are for large n, actually. Cool. Thank you. Yeah, that's a good question. So, okay, so let me go to a random order case first and explain you a little bit I mean, the situation is not so difficult. So this is a way, I don't know if you've seen it. You've seen proofs of the 1 over E guarantee for the secretary problem. But this proof that I haven't seen elsewhere is what actually gives the idea of our algorithm. It's very simple proof. So this is the proof. So we assign uniform random times to the elements in the interval 0, 1. So these red circles denote the arrival times of in the interval 0, 1. And now consider an algorithm that does nothing until time x. And starting from time x, picks the first value that's larger than the history set at that point. So you can easily compute the probability that this algorithm stops by time t. Why is that? Because you stop by time t bigger than x, of course. You stop by time t if and only if you have stopped by time t, if and only if the maximum element between 0 and t is in the interval xt. If the max is before, then you would not stop. If the max is after, then for sure you stop. Right? So this is an if and only if. So the probability of stopping before t is just 1 minus x over t. Now, you can also estimate the probability of getting the max condition on stopping at time t. And this is just t, actually. It's actually greater than or equal, but in the limit is equal to t. It's actually just t because like I have the maximum of an interval of size t, and I wonder how likely is that this guy is the maximum overall. Well, it's just t, right? Because the distribution of the maximum is uniform also. So after doing this, you just compute the probability of the algorithm getting the maximum, and you realize that this quantity, you maximize over x, and you get 1 over e. So very simple. And one cool thing about this proof is that n is never appears. It doesn't matter how many values you have. So that's, I guess, getting into Siamak's point. Doesn't appear. You can actually prove better guarantees if you have small n, but this proof works for arbitrary n right away. And this is the idea for our sampling p again. It's the same idea. So now, how does it work? We assign again uniform random times to each element. If the random time in 0, 1 is below p, then we just put the element in S, which is exactly, I think, what Nick was saying a minute ago. Otherwise, we put it in P. And, and the elements in V are revealed in the order of the tau values. And this is a uniform random permutation. So what's going to be our algorithm? Our algorithm is going to be extremely simple. It's going to be a fixed sequence of thresholds, T1, T2, and so on. And the algorithm, which is indexed by this sequence, will do the following. If some value arrives at the time that is between tk and tk plus 1, we accept it if it is a local maximum, so a maximum among what we have seen so far in V, and greater than the kth largest sample in S. So the order statistics in S is k or more, right? So I mean, you need this k, or I mean, this looking at the ranking in S, you need to look at it because maybe P is very large, and you cannot expect to get something that's larger than everything in S. That's unreasonable to expect to get something very large there. But it is reasonable to get something larger than some kth, like, I don't know, the 10th or whatever, even if P is large. So that's the algorithm for a fixed sequence. So that's ALT. And now if you think about it, analyzing this algorithm is very much in the spirit of what I just did for the secretary problem. I mean, okay, the math gets a bit messier, but there's nothing fundamentally hard in doing that. You just compute all these probabilities, condition here or there, and do the right integrals, and you get the values. And what's very cool is that we get that there is a universal sequence, a sequence T star, that is independent of P and N, such that alt T star obtains the best possible success guarantee. So the sequence of T's, it's independent of P and N, is fixed. And why is this? Well, it comes from from doing the math, basically. So if you do the math, and you can compute the success guarantee of the algorithm as this quantity here. And you get that the problem is separable and concave. So you just need to look at first order conditions, and the first order conditions are independent of P. Very nice. So you get a sequence T star, and this sequence gives you the optimal guarantee. So the other step that you need to do is the first line in my slide, is that proving that for any sequence T.
Hey, Jose, can I slow you down for a second?
Yeah, sure.
Sorry, on the previous slide, I missed what is T star.
Oh, T is a fixed sequence. Like I'm in principle, so this is like the summary, right? My algorithm is going to be indexed by a sequence T. Mm-hmm.
So T star is a vector of the optimal sort of switching times.
Yes.
Oh, I see. And then you were saying what, it's a constant in the next So the next slide now, just moving forward.
Yeah.
So you're still, T star is still going to be a vector. You're saying that vector doesn't depend on P and N. Is that
Yes.
what?
So T star is the solution of this maximization problem, maximizing this thing. So this quantity here is the probability that the algorithm succeeds.
Yeah.
Okay, you can like do the math and I mean, in a similar way to what I showed you before. So this is the probability that the algorithm succeeds. And now you basically need to solve this problem, but this problem is concave and it's separable. So the TIs do not depend on each other. So you just solve it. You just write down the first order optimality conditions for each variable. And which are these conditions, these equations here. And that's it. So now you have your optimal T stars, and there is one step that I missed somehow, which is the fact that if I fix T, the success probability decreases with N. I think this is what Siamak was asking earlier, right? So my worst case is when N is very large. So the guarantees I'm getting for these T's, I just need to look at what happens in the limit when N goes to infinity, and these are my guarantees. Okay. Okay, but this proves that you, yep.
Can you comment on the intuition of the algorithm? So it seems that at times move forward, you lower your threshold essentially, so you become less picky.
Yeah. So exactly. So you always want a local maximum, so a maximum in the set V, because if you don't have a maximum in the set V so far, then chances that you have the maximum overall in V are 0, right? So that's for sure. You always want that what you're picking is maximum from V, right? That's for sure. And now the question is, how do you use the set S, right? Early on, if you are early on in the game and your set S is not so large, you really want that your element, let's say as P is less than 1 over E, for instance. Okay, think of that case. So P is less than 1 over E. So now you have your interval 0, 1 thing, and then your P is below 1 over E. So you're here, you're below 1 over E. Yeah. And let's say X is 1 over E, right? Now you will not do anything until 1 over E. So basically you don't even look at P. So what you will always ask is for a guy that's larger than everything in P. Everything in S in the beginning, right? I'm not sure you're following me, Santiago, what I'm saying. Yeah. But if P, but at the end of the game, you start relaxing that condition, right? So now think that S can be very big. S can be pretty much like, I don't know, 2/3 of the values or something. If you're waiting for something that's the maximum in S, then you're gonna wait forever. Basically, you're never gonna get it. Like it's much more likely that the maximum is in S than outside S. So what you do is that you start relaxing this, and you have these times that tell you how to relax this. So these times, TK says, okay, from TK on, I'm willing to accept a value that's a local maximum, of course, and also only within the K largest elements in S.
Yes.
Like this doesn't apply if, like, say S is empty. If S is empty, this just doesn't say anything. So it just tells you, you take a local max always. Don't forget about it, right? And T1 is actually 1 over E, like, just to make it sure that you guys see that part. So T1 is 1 over E. So from 1 over E, you start doing anything. Before 1 over E, you still don't do anything.
So just a clarification on that point, if we think of the P equals 0 case, which is just a regular secretary problem, the version I'm familiar with says look at fraction 1 over E and then pick the local maximum that follows, right? Your version is actually different. There's some probability you could just pick the first element.
Yes.
And but those two are for large N are basically the same.
Right, yeah, so this comes from my, sorry. If think of X being 1/e here, if there are many red dots, these are the same thing, right? And if there are few red dots, your algorithm is better than mine.
But
yeah, that's clear. But in the worst case, the worst case comes when, but my algorithm is still better when there are few red dots than when there are many.
Right. So your algorithm still provides the same guarantee in some sense.
Right. Worst case guarantees is still the same, right? So my algorithm, both algorithms are equally good when n is very large. I mean, it's natural to believe this, right? And when n gets smaller and smaller, your algorithm is better than mine, but mine is still better than myself in the limit. Yeah, so in the worst case, we are in the same situation. Yeah, so this is not, yeah, so what I'm explaining here, so this algorithm ALT is not the optimal algorithm for any n. It is the optimal algorithm for very large n, and it only gets better when n is smaller. Cool, so yeah. So it's still optimal in the worst case. Okay, so this was my actually first sentence that maybe I should have mentioned earlier, right? So the success probability of ALT decreases with n. So it's getting worse and worse as n increases. Okay, so to prove it's best possible, it's a bit more technical, and but you can still do it. So maybe I'll skip this now, and if I have time, I go back to this in the end, because I want to be able to mention a little bit about the adversarial order case. Okay, so the algorithm for the adversarial order is actually very simple. So you use the following. So you take your set S, and you use an algorithm of a K-max algorithm. So K-max is the following. I look at the kth largest element in S. This is a fixed threshold, and I stop the first time I see something bigger. That's going to be my algorithm, with a specific K, of course. Okay, if S is less than K, we just accept the first thing we see in V. And if S is N, I mean, this is a problem of our model. Like, it could happen that there is nothing in V, right? So then we say, I mean, for large N, it's not very important, but here we will say we lose for the talk, but in the paper we say we win, which is worse for us. So you can do either and you get the same. Okay, so the guarantee, the optimal guarantee, you get it for this specific value of K. So think of P equals to 1/2. So then K is actually 2, and the guarantee is 1/4 in that case. Okay, so if P is equal, and then in the limit is 1/e, this guarantee. When P goes to 1, this is 1/e. So how this is done? Okay, so suppose that we sample out of the top K elements. So let's try to analyze the algorithm first. So we're going to use a K-max algorithm. So suppose that we sample K-1 out of the top K elements. And also we sample the K+1. So we have all these values, and we sample K-1 out of the first top K, and also the K+1. So let's say K is 3, this guy is sample, and out of these 3 guys, here we sample 2. So then the algorithm will win, right? For sure. Because our algorithm is the K-max algorithm. So we look at our values in S. So K is 3 here. We have 3 values. This is our threshold, and we'll only stop when we see this value. Right? So this is, then we're guaranteed to win in this situation, in this particular situation. And therefore, our probability of winning is at least what we get if this happens. Now, what's the probability that this happens? Okay, we need to sample this guy, which is the k plus 1. So that happens with probability 1 minus p. Wait, is this wrong on what I'm saying?
It happens with
No. That's fine. So the probability that this happens is actually k times p to the k times 1 minus p, right? So I sample these k guys. I didn't sample one of these guys, and there are k possibilities for the one I didn't sample, which could have been anyone from the first to the kth, right? So the algorithm succeeds with at least this probability. I pick the right k, which is the floor of 1 over 1 minus p, and I get my guarantee. Cool. Now, if you have this algorithm, now what if you have this algorithm? Now the adversary, what the adversary needs to do is to present. So, okay, so here's my point. So proving that this algorithm has this guarantee is very easy. Proving that this is the best possible algorithm is much harder. So how do we prove that? So think that the algorithm will present the elements in increasing order. So if the algorithm presents, if the adversary presents the elements in increasing order, the guarantee we just show you is going to be tight, because you're going to win exactly in this case. Anything different, if anything different happens, then you will lose if the adversary is presenting the values in increasing order. The problem is that if you know that the adversary will present, like you can now take the role of the adversary, think about it, the adversary will present my values in increasing order, so then now I'm going to change my algorithm and I'm going to just pick the last element, right? And now I'm going to win. Great. So this idea doesn't work directly. So what we do is the following. The adversary could do the following. Pick some n0 smaller than n and present an increasing sequence until time n0, and from there on present just zeros. Right? If the adversary presents this increasing sequence until time n0 and then zeros, what I need to do is to guess the last element of the increasing sequence.
Sorry,
I don't know. Yeah, sure.
I thought the adversary was just presenting the elements of V in an order of their choosing. So are we assuming?
Yeah, the adversary chooses the order. Yes, the adversary chooses the order. Yes.
But now you're saying they can present zeros. Right, so
no, it chooses the values as well. Yeah. The values are also chosen by the adversary. Yes. The adversary chooses everything.
They would have had to have fixed the alphas beforehand. So you're saying, I mean, n naught is not a choice of theirs.
Sorry? N0 is also a choice of the adversary, right?
I thought the adversary chose the values alpha 1 to alpha n.
And the order.
And the order.
Yes, exactly.
But then n0 would depend on the set S, right?
Well, no, because like, well, a little bit, yeah, but I mean, there is, okay. Yes, I agree, but so this can still be made, but you still don't know it, right, as a player.
Mm-hmm.
Yeah, so exactly, yeah, I agree with you, Nick. So thank you for the clarification. So the adversary will choose a set of values, which is an increasing sequence until some time that you don't know and as a player, and then zeros. Okay, and now you sample. And you see, and you also see in your sample set an increase in sequence and then zeros, but you don't know whether the next element is going to be larger or a zero. Right?
Yeah.
Right. So that's the game we want to play to prove that this algorithm is optimal. Right. So now basically, so all this boils down to a new problem, a new secretary type problem in which the player does not know n. Okay, so this is the way to prove that this is optimal. So let me just explain the problem and then I'll finish because I'm going over time already. So So the problem to which you reduce is the following. It's what we call the last zero problem. An adversary chooses an integer n now, and the referee writes a 1 or a 0 on each card with probability p or 1 minus p. Okay? The referee tells you the number of ones. So this is tells you the number of ones and p, but not n. So n is the increasing sequence. Your ones are your samples. And the zeros are the values you did not sample. You don't know how many zeros are there. You just know how many ones are there, right? The increasing sequence of the increasing part of the sequence. And you want to stop in the last zero. And the last zero. So I start showing you cards. Like if there are too few ones still, maybe you don't stop because you want to see more ones because you know there are 14 ones in the sequence. But once you've seen 12 ones, and I show you a 0, maybe you say, you know what, P is 0.73, and I have 2 ones left, or maybe this is the last 0, maybe I stop. So you want to maximize the probability of stopping at the last 0. Is that so? I mean, we can write the right connection between these two problems, and then we analyze this new problem. And for this last 0 problem, you can prove that this is the optimal guarantee, and basically there is some analysis on a conflict graph that I can explain you offline if you want. So sorry, my talk was a bit longer than I had thought. Anyhow, so this is an instance of the game, and this is a proof sketch, and then I think I can finish here. Thank you.